Section 3.5, Rational Functions. We're going to start off by defining rational function. A rational function is a function f of the form p of x divided by q of x, where both p of x and q of x are polynomials. So remember, another word for rational is just fraction. So this is a fraction with polynomials in the top and the bottom. Let's start by looking at the reciprocal function f of x equals 1 over x. So you can see it here graphed on the screen. Our domain is from negative infinity to 0, union 0 to infinity. So that means at 0, my graph is undefined. The range is kind of the same, negative infinity to 0, union 0 to infinity. So whenever we get to 0 on the y-axis, my graph is undefined. What happens at those two spots are called asymptotes. I have a horizontal asymptote and a vertical asymptote. We'll talk more about those later. Over on the left, you see a table of values, so that's how I got my graph. It's important to notice that 1 over x decreases the entire time. So if we trace from left to right, we are always decreasing. We also see that 1 over x is discontinuous at x equals 0. So as we're tracing from left to right, we have to pick up our finger and move it to the top to continue to trace. The x and y axes are my asymptotes here. And f of x is an odd function, and its graph is symmetric with respect to the origin. The next function that we're going to look at is f of x equals 1 over x squared. Anytime you see a function like this, I want you to think about a volcano. Because look at this graph. It's going to do what we call volcano. Instead of these two arrows going opposite ways like they did in our previous example, they're actually going to go the same direction. So we have our domain the same, negative infinity to 0, union 0 to infinity. So we're not defined on 0 because, again, it's an asymptote. And then our range this time is just from 0 to infinity, since our graph, both arrows are going up. This graph increases on the interval from negative infinity to 0, but it's decreasing from 0 to infinity. Again, my graph is discontinuous at 0 because that's where my asymptote is. And the y-axis is our vertical asymptote, and the x-axis is our horizontal asymptote. Let's look a little bit closer about what happens with graphs whenever they come near an asymptote. So as you can see, as my graph approaches x equals negative 2 from the left, it's going down to negative infinity. Likewise, as my graph is approaching negative 2 from the right side of the graph, it's going up to positive infinity. Same thing around 2. So what happens at asymptotes is our graphs either shoot up to infinity or they shoot down to negative infinity, which is something we'll kind of have to figure out as we're graphing. But it's just a line that my graph is going to get closer and closer to as it goes to infinity, but it's never going to touch it. It's never going to cross it. Now we will find out later that we could cross over an asymptote somewhere around this part of our graph. But the main thing is that when we have our arrows, it's those parts that get really close to the asymptote but never quite touch them. More formally, we define asymptotes like this. If our y value goes to infinity, so shoots up, or shoots down, because it has absolute value of my y value, as x goes to a, so as x gets closer to some number on the x-axis, then x equals a is our vertical asymptote. Likewise, if my y value goes to a certain number, say b, as the absolute value of x goes to infinity, then the line y equals b is a horizontal asymptote. Okay, let's talk about how to find asymptotes given a function. So first of all, in order to find asymptotes, we need our rational function to be in lowest terms. So we'll see an example at the end of our notes where we first have to simplify something out of the numerator and the denominator before we can look for asymptotes. So first type of asymptote we're going to talk about is vertical asymptotes. Remember, vertical is like this, so they are always x equals a number for the equation. To find these, we're just going to set our denominator equal to 0. So we want to find out what x values makes my denominator 0, which we all know we can't have. That's why there's an asymptote at that point. Next, we're going to talk about horizontal asymptotes. Horizontal lines are like this. So our asymptotes, when we're talking about the horizontal, are always going to be y equals a number. So we have three scenarios here. We're going to look at the degree of the numerator, p of x, and we're going to look at the degree of the denominator, q of x. Remember, degree is just the highest exponent. So our first scenario, if the degree of the numerator, p of x, is smaller than the degree of the denominator, q of x, then my horizontal asymptote is just at y equals 0. If the degree of the numerator is equal to the degree of the denominator, then we're going to take our leading coefficient divided by leading coefficient. So the leading coefficient for the numerator divided by the leading coefficient for the denominator. And then my third option, if the degree of the numerator is bigger than the degree of the denominator, then we don't have a horizontal asymptote, but we might have a slant asymptote, which I'll talk about on the next slide. Slant asymptotes, also known as oblique asymptotes. If the degree of our numerator, p of x, is just one more than q of x, then we're going to have a slant asymptote. To find this, we divide the numerator by the denominator and we disregard the remainder. Make a note here that we're going to be using synthetic division for that. Set the rest of the quotient equal to y to obtain the equation of the asymptote. So this asymptote is going to be a slanted line, something like this. It will be in the form y equals mx plus b. Here's an example of a graph that has a slant asymptote. So the graph of f of x is shown in red. You can see we have a vertical asymptote and a slant asymptote. The slant asymptote is at y equals x plus 2. Example 4. For each rational function, find all asymptotes. We're going to start by finding our vertical asymptote, and to do so, we're going to set our denominator equal to 0 and solve. Our denominator here has already been factored for us, so it's just going to be a matter of using the zero product property. So since two things being multiplied equals 0, I know I can set each of those pieces equal to 0 and solve. So this graph has two vertical asymptotes, one at x equals 1/2 and one at x equals -3. To find our horizontal asymptote, we're going to look at the degree of p of x, which is 1, and the degree of q of x, which is 2. Now, we know that the degree of q of x is 2, because if I were to do FOIL or box method, I would end up with the first term being 2x squared, so degree 2. Since p of x degree is less than q of x degree, I know that I have a horizontal asymptote at y equals 0. We know that we don't have a slant asymptote because the degree of p of x is not one more than the degree of q of x. Example 4, we're going to find all asymptotes for f of x equals x squared plus 1 divided by x minus 2. To find our vertical asymptote, we're going to set our denominator equal to 0 and solve. It's really important here to remind you that your answer should be an equation of a line. So it should say x equals a number. If you ever just tell me your asymptote is at 2, then that isn't specific enough to be able to graph it. For the horizontal asymptotes, we find that p of x has degree 2, q of x has degree 1. Therefore, we do not have a horizontal asymptote. Now we're going to find our slant asymptote. Since the degree of the top is just one more than the degree of the bottom, we will have a slant asymptote for this example. So the way we find it is we divide the two polynomials and we disregard the remainder. So remember synthetic division. I've changed my 2 from a -2 to a +2. And I put a 0 in my list of coefficients on the top because I'm missing an x term in the numerator. Now I bring the 1 down, and then I take 1 times 2, and I put that below the 0. I add down again, multiply 2 times 2, I get 4. Add down again, I get 5. We're going to disregard the remainder, and then write the 1 and 2 as my slant asymptote.